as Nicky said, I've been a volunteer for over 3 years, and I've seen a lot of interesting stories. But there's one story which I haven't seen yet, which I think is a very interesting story. So that's what I want to tell you about today. And this is about how we measure distances in the universe and the concept of the cosmic distance ladder. And coincidentally, a few months ago, one of the greatest mathematicians alive collaborated with this YouTube channel, 3 Blue, 1 Brown, to also make some YouTube videos on this topic. So part of the talk is inspired by these YouTube videos, but if you want to know more details, look those up. Yeah, so measuring distances on the Earth is straightforward. You can basically just walk somewhere and try to get an estimate of how far it is. But in space, this is much more difficult. We can go to the moon, but that's about it. And therefore we need to come up with new ideas on how to do this. So I'm going to first start with a very complicated slide. You don't have to understand anything of it, other than this is a slide I once got in one of my lectures. And it's basically many methods on how to estimate distances in the universe. Of course, I'm not able to cover all of these, so I'll try to give in a perspective, both historically as well as a modern perspective. So the first thing you might wonder if you want to estimate distances is about the size of the Earth. This is the first astronomical object. So this is what the Greeks already wondered, and they were actually able to do this. But before you can actually wonder about the size of the Earth, you first have to infer its shape. And as far as we know, the first person to write this down and realize this is Aristotle. And the way in which they do this is they actually used lunar eclipses. So what happens is that the Earth is in between the moon and the sun, and as the sun shines on the Earth, it leaves a shadow on the moon. And when you then look at the moon, you see some kind of circular patch on the moon, for instance this patch. And if you combine all these images, in this case actually it's somebody from Australia who made a clever image, you see already that the moon is circular. And Aristotle realized this, that wherever you on the Earth you look to the moon, the shadow is always circular. And this is only possible if the object, the Earth, is a sphere. The sphere is the only object whose shadow, whose projection is always circular. The second thing that they could already use from this is actually the relative size of these objects. From this you can already see that the Earth must be bigger than the moon. So they could also use this. Okay, then the actual size of the Earth was also done by a different Greek around 200 BC. And for this they used something which we refer to as a geometrical method. This is a method typically using angles, cosine, sines. It's something you can probably understand with high school maths. And that's also why the Greeks were already able to do it. So the story is as follows. One day this Greek guy, Aristophanes, he was walking in the city of Syene, and he looks down the well. And when he looks down the well, he sees that there's no shadow at all in the well. And what this means is that the sun is directly above the well. Now at the same time, there is a different guy who is in a different city, Alexandria, and he has stuck a rod perpendicular in the ground, and he sees that the rod leaves a shadow on the ground. And from the shadow, the size of the shadow compared to the size of the rod, you can infer the angle that the sun has with that rod. And then he realized that this angle, which is also here, must be, gives you actually the distance between these two cities. And they could also measure these two cities. And if this angle, which in this case was 7 degrees, we also know that the entire circle is 360 degrees. So by multiplying those, he could get to an actual estimate of the size of the Earth. Now the way in which he actually measured that is not entirely clear. There's stories about boats going, there's stories about slaves having to walk the entire distance. But it's generally accepted that they were accurate to within 10%, which is quite impressive. And what's even more impressive is that this one slave walking from Alexandria to Syene is in principle the only direct measurement you need to estimate the size of the universe. So we'll see that from this measurement, the size of the Earth, we can go to the size of the solar system, which will give us this distance to stars, the distance to other galaxies, and in the end all the way the size of the universe. Yeah, so this is the size of the Earth. Then the next thing you might wonder is, well, how far away is the moon? And for this we can again use an eclipse, and this was done by a different Greek guy, Aristarchus of Samos. And for this they again use the solar eclipse, but now actually the duration of the solar eclipse. So when a solar eclipse happens, the moon moves into the shadow of the Earth, and approximately 4 hours afterwards it leaves this shadow again. And we know that the size of the shadow must be roughly the diameter of the Earth, 2 times the radius. And at the same time, we know that the entire circle that the Moon goes about the Earth is 28 days. So from this, they could get an estimate of the distance to the Moon. Now these calculations are all very approximate, as you need to carefully consider what it actually means for something to be in the shadow. Does it need to be in the shadow completely, or only partially? And at the same time, the orbit is not fully spherical, but elliptical. However, for this example, the prediction would be 53 times the radius of the Earth. And in reality, we now know it's roughly 60 Earth radii. So again, it's pretty accurate. So the way in which we measure these distances nowadays is actually by mirrors, which the Apollo astronauts left on the surface of the Moon. So you can see a picture over here. So what they do is they send bundles of light to the Moon, and these mirrors reflect part of them, and we can catch them again to estimate the distance. And for this you need to carefully know the speed of light, which we nowadays know from laboratory experiments. And when you do that, you get something like this. You see oscillatory patterns with both very high frequencies, so very quickly moving oscillations, as well as more longer wavelength oscillations. And so these shorter ones are actually due to the orbit of the Moon around the Earth being elliptical, and while the longer ones are due to the orbit of the Earth around the Sun and the secondary influence of the Sun on this orbit. And from these accurate observations, which in the best case are with millimeter accuracy, we now know, for example, that the Moon moves away with roughly 4 centimeters per year. And as I said, to be able to do this, you need to know the speed of light with great accuracy. And now, as a side note, the first measurement of the speed of light was actually also made by astronomers. And for this, they could use the orbit of Io around Jupiter. So Io is a moon of Jupiter. What you see over here is a picture I took with my phone a couple of months ago at the old observatory. So I held my lens against the telescope, and what you're seeing, this blue circle, is the aperture of the telescope, basically. It's just evening, so it's not dark yet. And then you can see Jupiter, as well as 3 moons, and where the closest one is Io, probably. So this is also what they could already see roughly 400 years ago when they had built these telescopes. And what they saw is that Io moves around Jupiter quite quickly. It takes only roughly 2 days for Io to move around the planet. And therefore they could predict with great accuracy when it would move in the shadow. And then they noticed something peculiar, namely that in one season, for instance the winter, Io would appear to be a few minutes late, whereas in summer Io looked to be a few minutes early. And they could not really understand this until this Danish guy, Ole Rømer, came up with the idea that it must be because the Earth is on different sides of the Sun in these different seasons, and Jupiter is, in both cases, still on the same side. So let's say that the Earth is on this side, then the light will have to travel a shorter distance than when the Earth is on the other side. And from this, they could then actually estimate, using the time difference, which is roughly 12 minutes, estimate this speed of light. Now, it was not accurate at all yet, because they didn't know the distance between the Sun and the Earth, but it's still an impressive feature. Okay, so then we know the distance to the Moon, and then the next step is to actually get the distance to other planets, or to the Sun, basically the size of the solar system. And this is slightly more complicated. Until now we have assumed spherical orbits, but this is no longer possible in this case. And then it gets really more complicated, because in essence the only thing we have is the Sun, and the Earth rotates around the Sun in some unknown elliptical orbit, and at the same time the other planets rotate in some unknown elliptical orbit around the Sun. And yeah, it's much more difficult. It's an entirely different AOT talk to explain how this is solved, but basically thanks to Kepler, he was able to determine the actual shape of these orbits as well as their relative shapes. So for instance, that Mars is on average 1.5 times more further away than the Earth. And then they only needed one distance to a planet, or the Sun to a planet, to basically pinpoint the entire size of the solar system. And this was then thought up by Edmund Halley. He wasn't able to do the calculation himself, because for this you actually need a transit of Venus. So this is when Venus transits in between the Earth and the Sun. You can see a small shadow of Venus on the surface of the Sun. And how you can use this is if you have two different observers on two different locations on the Earth, so the north and the south in this case, and they both look at Venus, and they see two slightly different things. So in this case, the southern observer sees Venus in the northern part of the Sun, whereas the northern observer sees it more south. Now, and in this case, this is greatly over-exaggerated. In reality, this difference is very minor. But they were still able to use this transit. And they couldn't take pictures yet because those hadn't existed. So the way in which they actually did it is by counting the time it took for these for Venus to pass, and that gave them an angle in the end. And from that end distance between north and south, so the size of the Earth, we can then get to the distance of the solar system, so the distance to the Sun. This is the next step on this cosmic distance ladder. And this is the first example of parallax. And the idea of parallax is that the relative change in positions between two different observers gives information about the distance. So a standard analogy you can take for this is when you're driving in a car across the countryside, you see that the trees which are close by move away very fast, whereas the distant mountains only go very slowly. And by the speed with which these trees move as you drive, you can get an estimate relative to the mountains, how far they are. And the same thing holds if you are on two sides of the Earth, you look at Venus and you see some difference. That's how we get the solar system size, and then to get the sizes or the distances to other stars, which is the next step, we use exactly the same idea, but now not on two different sides of the Earth, but on two different sides of the Sun at two different seasons, so summer and winter. Whether the Sun is here, or whether the Earth is here, or whether the Earth is here. Then you can also see that a close-by foreground star moves relatively quickly compared to those background stars, which are much farther away. So an example of this is shown over here. So this is Proxima Centauri, which is the closest star to the Earth. So it has the biggest parallax, the way we call it. So its movement should be the greatest, and as you can see in this animation, it's pretty clear. But in reality, the actual movement on the sky is about the thickness of a hair on 10-meter distance. So it's something you can't see by eye. You need really accurate instruments to be able to do this. But they were able to do this, and actually for the first time this happened roughly 200 years ago by Philip Bessel for this star 61 Cygni. And to me this is quite impressive that only 200 years ago we were able to measure the first distance to another star, and now we already know the size of basically the size of the entire universe. Now, in 1998, roughly 35 years ago, they launched the first satellite, which was dedicated to using this technique to measure the distances to close stars. And here is an artist's impression of the Milky Way, and this small yellow speckle is basically all the stars that Hipparchus was able to see. Now then, roughly 20 years later, they launched a new satellite, Gaia, and it was doing exactly the same, it was just much more precise. And what Gaia is able to see is this. So Gaia has by now collected all its data. A few months ago it retired, but when it's going to do its final data analysis, it will basically be able to cover the entire Milky Way. From covering this, Gaia could in principle get an estimate of the size of the Milky Way, but they were already able to do this before with different techniques. So we now have the distance to a star, and we're going to go to the size of the Milky Way. And to be able to do this, we need to introduce a new concept, which we refer to as a standard candle. So a standard candle is an object from which we can observe its brightness, so how bright it is on the sky. And we can in some way also infer how bright it must have been, well, at the emission basically, so how bright it is intrinsically. And when you know the apparent brightness and you know how bright it actually is, you can scale it by the distance in order to match those two. And in that way you get an estimate from the distance. And so one way to do this is by using this complicated plot. So what's shown here on the y-axis is the luminosity. So this is the intrinsic brightness, which you can get from the distance and the apparent brightness. And what's on the right hand, or so on the x-axis, is what we refer to as a color. It's a proxy for the temperature, and it's basically comparing how much red light and how much blue light does a star emit. If it emits a lot of blue light, it's typically hot, and it will be on the right of this figure. If it's redder, it's on the other side. And similarly, if something is very bright, intrinsically it will be on the top of this plot. And so what they did is that for the stars which are close to the Earth, for which you can actually measure the parallax, you know the distance, and then you can also get the luminosity from the distance you know and the apparent brightness, and then they plotted this luminosity versus this color. And then you get something like this, and as you can see, it's not at all uniformly distributed. There's a clear structure between different groups of stars. Now, if you then have another star which is slightly further away, for which you can't use this parallax because it's too small, your instrument is not sensitive enough, you can then still measure the apparent brightness, and you can measure this color, and then you can scale the distance such that it will fit on this on the correct line in this plot. And that then still gives you an estimate of the distance. And as you can see, it's more complicated because there's multiple curves, and you still don't know, you might not know to which group it actually belongs. But to be able to do this, they actually use the entire spectrum of stars. So that's what's shown over there. It's the intensity for different colors of light, basically. And I think this is for the sun, and you can see that there's specific absorption lines. And we know that these different groups all have different absorption lines, so that way you can identify the group to which an object does belong. But yeah, this is the first example of a standard candle, and this helps us to find the size of the Milky Way. Then the next step is to go to other galaxies, and for this we can again use a different standard candle, maybe Cepheid variable stars. So this is a star which was discovered by this woman, Henrietta Swan Leavitt. And she noticed that when she looked at one of the satellite galaxies of the Milky Way, to the Small Magellanic Cloud, that there were a bunch of different stars which were flickering with a certain brightness. And when she measured both the brightness, so how bright it was, as well as the time in which it oscillates, she noticed that there was a strong correlation between these two different observables. And that means that we can use that to then infer the distance. Because the period, the time it oscillates, then gives the intrinsic brightness, and we can again look at the observed brightness and then scale those in order to get the distance. Now, however, to be able to use this, you again need to calibrate it using local Cepheid stars, for which you can get the distance in a different way, namely this parallax method again. So this parallax method gives us the Cepheid, calibrates this relation, and and this was actually done by Hubble, for example, to determine that the Andromeda galaxy is an entirely different galaxy, and it's not just in our own galaxy. And this for astronomy was a major breakthrough because it determined that the universe is much bigger than we actually thought before. And then the final step to be able to actually go across the entire universe is using redshift. So this is what Lucy will probably also use in the second talk. But what actually happens, well, you're all familiar with the concept of redshift because it's basically a Doppler shift. If an ambulance moves towards you, you hear something different than when an ambulance moves away from you. And this also happens with the light from galaxies. And now as the universe is expanding, we know that in general more distant galaxies experience a stronger redshifting. So when these absorption lines are more shifted, and therefore we can use this. However, to be able to actually use a distance, this needs to be calibrated again by determining the distances in a different way. And this is the entire concept of the cosmic distance ladder, that you can calibrate this redshift relation by getting the distances of these distant supernovas, which are calibrated using the Cepheid variable stars, which we just saw, which are calibrated using the parsec methods, which were based on the distance between the Earth and the Moon, which was based on the Earth and the Sun, which was based on the size of the Earth. And then you can use this method to go basically all the way back billions of years to when the universe was a few hundreds of thousands years old. And this then gives us the entire structure and basically evolution of the universe. Then to conclude, I want to mention one different way to measure distances, which is a much more relative, new relative observable, and that is standard sirens. So this is using gravitational wave mergers. So when two very massive objects, neutron stars or black holes, when they merge, they send out some ripples through the fabric of space-time. And when we measure this using laser interferometers, it looks something like this. And from this frequency pattern, we can determine roughly how massive these objects were, and also how high the signal must have been originally. And if we then compare it to what we observe, you can get a different estimate of the distance. And this is very useful because it's basically independent of the entire set of steps we just took. So if you then can compare these two methods, you can get insights on whether your theory is correct, but also on whether you might have made a mistake somewhere in the first step of the ladder that then propagated all the way through to the final step. Yeah, so this is my talk. This is, well, thank you for listening. Any questions?
Yeah, so you said that the galaxy could be measured, the size of the galaxy can be measured, but sometimes we also hear that the galaxy is infinite. Is there a reason to believe that the final statement is false, or can you indeed measure the whole galaxy, or is it infinite? What is it?
Whether the size of the galaxy is infinite?
Like is the galaxy infinite? Universe, I'm sorry, the universe.
We don't know whether the universe is infinite yet. We can only see as far as the light has traveled since the Big Bang, which is roughly 3.7 billion years. And we don't know. Yeah, that's the honest answer.
So it isn't?
We don't know.
I was curious about, well, I understand that this distance ladder is necessary for those low to intermediate distances. For high redshift, do we also require this calibration from lower distances, or are cosmological models sufficient?
Cosmological models are sufficient, but you need to calibrate your cosmological model parameters using some way. This is typically done, for instance, using supernovas, and then you need this entire step of distance ladder. You can do it in different ways, for example, from the CMB power spectrum, but yeah, they also find competing results, which may hint at that, for example, there's some calibration error in this ladder, although they wouldn't say so.
I heard that they also use pulsars. In which step of the ladder they use that?
I'm not entirely sure. The question was, I've heard they also use pulsars. In which step of the ladder is that? The picture in the showed in the beginning, this one is all the methods that you can use to use the Hubble constant. Let's see if there's pulsars in here. No, I don't know.
Right? Pulsar timing is very new, right?
Yeah, that's
So
right.
in there.
I don't know. Okay, I think it's time for a break then. So let's get another beer.